Welcome to 8.3, where we left off. In 8.2 was calculating intervals for a one proportion estimate for the population. 8.3 carries that same idea, but with means, when I'm trying to find the interval or estimate for the mean of a population. So you'll be able to tell based on the problem that you're talking about something with numerical data, for instance, height, weight, IQ score, SAT score, as opposed to the categorical data from last time, which put people or things into categories. So what candidate they favored, or whether they did or did not favor a certain thing that was coming up for a vote. That kind of topic was 8.2. So we're going to start off 8.3 with a slightly unusual, slightly theoretical estimate that looks very similar to what we did with proportions. So last time we had the point estimate for the proportion interval was p hat. So in other words, the p that we got from our sample. So our point estimate for means will be the sample mean. So if I have a sample average GPA, then I'm going to use that, my X bar here, in front of the plus minus. Then just like with proportions, my Z star value would come from my table and be based on just the confidence level itself. And then that would be multiplied by the standard error, which is the population deviation over the square root of n. Now notice this standard error is a little bit different from the proportion one, because we're talking about something with a mean and deviation, not something with the proportion, the p-hats involved. Everything after this plus minus, once again, is considered the margin of error. The thing that makes this a little bit more theoretical than the one that we did last time was that if we did in fact know the population deviation, we would have to know the population mean. And keep in mind that's what we're trying to estimate for our with our interval, is what the population mean really is. So I wouldn't generally know what the population deviation was without already knowing the population mean, which would make this whole process null and void. But it is a good kind of bridged example to talk about how we would do it if we knew the population deviation. There are a few instances where that would happen. For instance, like the standard IQ test has been taken by so many people over the courses of decades that we can use a generalized population deviation. We know that the deviation is about 15. Same thing with large, wide-ranging things. Height of young women or young men, for instance, or a normed test like the ACT or SAT, where it has thousands and millions of people who take it, could be some of the few examples where we would use this. So for instance, if I had a 95% confidence interval with a sample mean of 3.2, a population deviation of 5, and a sample size of 20, then I would just plug in each of those values into these symbols and come up with my interval. I can also calculate approximately how large my sample needs to be, in other words, solve for n, by putting this latter half of the formula, the margin of error piece, basically less than or equal to a given margin of error. That's what MOE stands for. So for instance, if I have this situation where I'm wanting to know the average cholesterol level of a variety of monkey that's going to be used in my experiments, I want to estimate the proper cholesterol level within 1 milligram. So if I want it within 1 milligram is what my margin of error is. I have a 95% confidence level, so that's going to influence what my Z-star value is that I get. And in this study, I have information from a previous experiment that gives me a standard deviation of about 5 milligrams. So I can plug that in, assuming that this experiment is very similar. I should have a very similar deviation. So I can plug in Z, sigma, and margin of error and solve for n. Here's what that would look like. So 1.96 is the Z-star associated with 95%. Plug in 5 for 5 milligrams and the 1 for the margin of error. Notice last time we had to change this into a decimal because we were talking about within a margin of error of percents, and now we're just talking about within milligrams, so that does not need to change units. First thing I would do is divide both sides by 1.96. That's where the 0.5102 comes from. Then I chose to multiply both sides by square root of n, divide by the 0.5102, that should have a point in front of it, and then square both sides to come up with my estimate for n. Now, even though this is a very small number, I'm going to always round up for sample size calculations, just like last time, because this is saying I need to sample at least 96.04 monkeys, or I need to experiment on at least 96.04 monkeys. I can't, of course, test 0.04 monkeys, so that since this is at least or greater than or equal to, that means I must round up, even though that's a very small decimal. So my answer would be that I need to include at least 97 monkeys in my experiment. Okay, the slightly more realistic version of that would be this slightly different version of the interval for means. So notice I still have a point estimate of x bar. This is my sample said my estimate for the population mean is, plus or minus my margin of error. Notice that I've switched now to a t-star value. That will be from the table, a different table, the t table instead of the z table, and it's going to be based on the number of degrees of freedom, which I'll explain in just a minute, and the confidence level. Then that is being multiplied by the sample standard deviation, because I'm now looking at the more realistic version of the problem where I don't know the population deviation, and I have to use both the sample mean and the sample deviation over the square root of n, which is my sample size once again. Now notice this illustration taken directly from the book kind of illustrates what the t-distribution looks like. The standard normal distribution is this solid black line. Then the red line, the red dotted line, is t with 2 degrees of freedom. The solid blue line is with 9 degrees of freedom. Notice it's much closer to the standard normal curve, this black one. And in fact, as the number of degrees of freedom increase, the closer and closer it will get to a normal distribution. That is important. Now, when I find my t-star value, it's based on two things. I mentioned this already: confidence level and degree of freedom. So confidence level we're used to. Degree of freedom is new. Degree of freedom is always one less than the sample size. So if I have 10 in my sample or my experiment, I would have 9 degrees of freedom. So we're going to need our t-table, so you may want to access that from your course information. Here are just some examples that we worked out in class. So if I have a 96% confidence level and I have a sample size of 26, notice that means I have 25 degrees of freedom. What I'm going to need to do is go to my t-table, table B. I had 25 degrees of freedom. So I'm going to go down to row 25, and then across the bottom you have the confidence levels. So I'm going to 25 degrees of freedom and over to 96% confidence level, and there is my 2.167. Now remember, with proportions we just used this last line, and it was just based on confidence level. This is just a little bit more complex. We have to look at one less than the sample size, and then over to the correct confidence level, and there is 2.167 would be the t-star that I would use in my interval. So 99% confidence for n equals 8 means I need to go to 7 degrees of freedom, scroll up, and then look at 99% confidence. So 7 degrees of freedom, 99% confidence, which will be this row right here, this column. So I get 3.499, and so on. So 90% confidence with n equals 50 just becomes a little bit more difficult because of lack of space in the table. We don't have 49 degrees of freedom, so you're going to go to the next highest one. So if I have a sample or an experimental group of size 50, and I don't have the option of going to 49 as a row on my table, I do need to use the next highest one. I don't ever want to go up, so I would use then 40 degrees of freedom, 90% confidence, and that's where the 1.684 came from. Okay, we try to check your understanding in class, so if you want to pause the video here, you can, to see if you can locate the the t-star values for these specific criteria. Okay, to carry on, we're going to take a look at conditions and the state plan to conclude of just an example or two here. So we have the randomness, normal, and independent conditions, just like with proportions, just how they're shown is a little bit different when we're not dealing with proportions anymore. You need to have either a random sample or a randomized experiment. You need to have, for the normality or the normal condition, you need to have a sample size of at least 30, so greater than or equal to 30, and that gives you that the shape of the distribution is approximately normal by the central limit theorem. If you don't have a sample of at least 50, you're going to make a normal probability plot. That is the sixth type of graph on your calculator. So you put your numbers into L1 and then hit stat plot and change it to the sixth graph, and you're looking for a graph that's approximately linear. If you have something that's between 15 and 29, you would say it's probably approximately normal, as long as there's no outliers or strong skewing. Anything less than 15, though, you really want to see a very linear pattern in the normal probability plot. Any kind of wave, whether it's in the middle or on the ends, suggests that the distribution is not normal. And then for independence, this is very similar to proportions. Either use a 10% condition if you're talking about a sample, or some statement saying that the results must be independent if you're talking about an experiment. Okay, so here's an example. You have environmentalists and others are interested in the pollutants, specifically nitrogen oxides. Researchers gather the NOx levels for a random sample of 40 light-duty engines. We get an average NOx reading of 1.2675 and deviation of 0.3332. Construct 95% confidence interval. Now, anytime you see that, even if it doesn't say use all four steps, you do need to do state plan to conclude to get full credit. So I want to construct a 95% confidence interval for the average NOx emissions in light-duty engines. Be as specific as you can. Plan, this is where I should have put in the type of interval. Okay, I put it down here in the do step. So it's a one sample T interval, or just plain T interval would be fine. The sample was randomly selected and can be considered independent because there should be at least 10 times the 40 light-duty engines out there. So 40 is less than 1/10 of all light-duty engines. You could also have stated that the NOx emissions of one engine should not affect another. That would have been fine. The distribution of samples should be approximately normal because the sample size is so large. I plug in my sample mean plus or minus my t-star value that I got from my chart. I had 40 in my sample size. The chart does not include 39, so I would have to go down to 30 degrees of freedom, and 95% confidence level. This is where I got the 2.042. Plug in the standard deviation and the sample size. There's my numbers that I get from the calculator. Then conclude I'm 95% confident that the interval between 1.16 and 1.37 or 375 captures the true average NOx reading for light-duty engines. Part B, they set a limit of 1.0 for this type of engine. Do I have evidence to suggest that it is below that? It is possible that the true average is below that, but because we have both ends of the interval well above 1, not below, we would say it would suggest that the light-duty engines are exceeding the regulation. Okay, here's another example. Go ahead and pause the video and try this one on your own. Okay, you have some numbers that you need to type into your L1. Do the state plan. This was just an example of how to do some of the stuff in the calculator. So there is a normal probability plot. You see that you have possible outlier, maybe one on each end, a little bit of wiggling. So you could say the normal condition is not met, or some concern with the normal condition being met, or proceed with caution. Do one sample T interval is just called T interval in the calculator, and then conclude as normal. Go ahead and try the solution set or the problem set for 8.3 and let me know if you have any questions.